Now, let's look at the same situation with the roller coaster, but assume that the initial speed is 5 meters per second as opposed to at rest. So we still have the before and after, and we still have the kinetic energy plus the potential is equal to the kinetic energy plus the potential. So we have 1 half mv I squared plus mg, we'll write it as yi, equals 1 half mvf squared plus mgyf. The mass still is not a factor, so we have 1 half. The initial speed is 5 squared, and it is still 20 meters in the air above the reference level that we used earlier. We're looking for the final speed, but in fact, since our final position is at the reference level, this goes to 0. So we have 25, half of 25 is 12.5 plus 20 times 9.81. And I'm just using the absolute value of it there because if we think about it, it's really the work done in elevating it to that. So the force was applied vertically. It's more like a tension. It's 1 half VF squared. So we know that VF squared is equal to 417.4 approximately. So we have a final speed of about 20.4 meters per second. A 60 kilogram person jumps onto the floor from a height of 3 meters. He stands stiffly with his knee joints compressed by about a half centimeter. Calculate the force on the knee joints. Okay, so all of the kinetic, all the gravitational potential energy for a 60 kilogram person, 3 meters in the air. E sub P is mg h or mg delta y. So it's 60 times 9.81 times 3. So what we're looking at is approximately 1,766 joules of energy. Now, all that energy is going to be dissipated in the form of work done on the knees by compressing them about a half centimeter. So the work is equal to the force times the distance. And a half centimeter is about 0.5 times 10 is, excuse me, not about, it's 0.5 times 10 to the minus 2 meters. So if we simply divide each side then by 0.5 times 10 to the minus 2, we end up with a force of about 353,000 newtons. And even if we were to assume that that force is divided over to 2 knees, it's still going to be painful. A toy car, with mass about 100 grams, is propelled by a compressed spring. The car follows a track that rises at 18 centimeters above the starting point, 0.180 meters. The spring is compressed 4 centimeters and has a force constant of about 250 newtons per meter. Now, we're not going to necessarily go into the details of springs just yet. This is kind of a heavy-handed idea to get you thinking about where the energy or the work is coming from. So we can say it's 250 newtons per meter times 4 times 10 to the minus 2 meters. So in other words, we're going to be assuming that it's actually doing about 10 joules of work on the car. So if actually applying 10 newtons of force rather over a distance of 4 centimeters. So in other words, about 0.1 joule of work. Let's try that again. In other words, we're going to assume about 4.4 joules of work. Assuming the work done against friction is negligible, how fast is the car going before it starts up the slope? All right, the kinetic energy. We'll say that this is not quite right, and it's not. We'll talk about it later. But I needed to go ahead and at least give you some value. All right, if we say that's 0.4 joules, which is 1/2 mv squared, then we have 0.8 joules is equal to 0.1 v squared. So 8 is equal to v squared, and that leaves v to be about 2.83 meters per second. It rises 0.18 meters. 0.1, 9.81, 0.18. So at the top, approximately 0.177 joules of energy out of the total of 4/10 of a joule are going to be converted from kinetic into gravitational potential energy. So at the top, E sub k is equal to 0.4 minus 0.177, which is going to be approximately 0.223, which is 1/2. The mass is 0.1 v squared. So at the top, it's going to have a speed of approximately 2.11 meters per second. And this you could look at and get a rough idea of what this car is doing. Now what this will show you is ignoring friction. This gives us an idea of what we call path independence. In other words, it could in fact still go through this loop and then come back up to that height, provided that the loop at the top was still below the level that the car started.